Modern digital infrastructure relies on high-velocity data streams, requiring systems that can process information the instant it is generated. Apache Kafka provides the foundational architecture that manages and distributes these high-velocity event streams across the modern enterprise. Despite its widespread adoption, Kafka's original design depends on an external coordination system that is now being phased out. This system is Zookeeper, a centralized service historically tasked with managing Kafka's cluster metadata, broker registrations, and leader elections. That external dependency is being deprecated in favor of KRaft, or Kafka-Raft metadata mode. KRaft removes Zookeeper by internalizing metadata management, using a built-in consensus algorithm to keep brokers synchronized. Understanding this shift is essential for architects who need to scale data pipelines beyond the limits of legacy coordination. Adopting KRaft represents a structural change in how distributed systems maintain and propagate their internal state. A legacy deployment requires two independent environments, a Kafka cluster and a Zookeeper cluster. Zookeeper coordinates distributed processes and stores metadata. When Kafka scales to hundreds of brokers, coordination requests increase exponentially. This creates a bottleneck. Zookeeper cannot process updates fast enough, limiting growth. Beyond these technical constraints, the dual system architecture creates significant operational friction for engineering teams. Maintaining two separate distributed systems forces administrators to manage two distinct security perimeters and two different sets of authentication protocols. This separation increases the likelihood of configuration mismatches, as human operators must manually ensure both systems remain in sync. Furthermore, a dedicated Zookeeper ensemble requires its own hardware resources, increasing the total infrastructure cost and maintenance surface. While Zookeeper solved early coordination problems, it has become the primary bottleneck preventing Kafka from achieving higher levels of scale. KRaft mode simplifies this architecture by removing the external dependency, leaving only the unified Kafka brokers. Without Zookeeper acting as the arbiter, Kafka must manage its own control plane internally. To achieve this, it designates a specific subset of its brokers to form the controller quorum. This quorum handles all the metadata and synchronization tasks that were previously offloaded to the external system. The mechanism that enables this internal coordination is the Raft consensus algorithm. Raft allows the quorum to elect a leader and reach agreement on the state of the cluster through a series of internal votes. This native election process occurs directly within Kafka, avoiding the network overhead and latency of external coordination. The result is a unified system where the data plane and the control plane operate within a single perimeter. By utilizing the Raft algorithm, Kafka manages its own state, removing the horizontal scaling limits imposed by external systems. Without an external database, the controller quorum needs a reliable method to store and update its metadata. In KRaft mode, metadata updates are written sequentially into an internal distributed log. This log uses the exact same storage format that Kafka already uses to handle standard user event data. Treating cluster configuration as a native event stream ensures that every broker in the quorum maintains a consistent view of the system. This design also improves how the system handles critical infrastructure failures. If the leading broker suffers a catastrophic hardware failure, the surviving quorum nodes must coordinate an immediate response to maintain availability. The surviving brokers immediately check the distributed log to access the most recent, consistent state of the cluster. The internal Raft protocol then triggers a new leader election, restoring the control plane much faster than a Zookeeper timeout would allow. Internalizing state management into a distributed log provides the control plane with the same fault tolerance and speed as the data plane. Transitioning a live production cluster from Zookeeper to KRaft requires a structured engineering approach. While legacy configurations remain supported for now, delaying the transition maintains existing security and performance vulnerabilities. Preparation begins with an audit to ensure all active Kafka clients and surrounding integrations are compatible with the KRaft protocol. Teams must develop a phased migration plan, identifying low-traffic windows to minimize impact. The execution involves an incremental transfer of metadata, allowing the new control plane to take over without a sudden cutover. Moving too quickly through this transition often leads to avoidable deployment failures. Skipping comprehensive testing in a staging environment significantly increases the risk of data consistency errors during the live migration. Furthermore, failing to account for legacy dependencies can cause a cluster to stall during the metadata transfer. Executing a KRaft migration as a staged structural transition ensures the control plane remains stable without risking data loss. KRaft eliminates architectural complexity, unifies security perimeters, and allows Kafka to scale horizontally without the constraints of external coordination. In financial services, the lower metadata latency provided by KRaft optimizes high-speed transaction processing and settlement systems. E-commerce platforms benefit from higher throughput, enabling real-time recommendation engines to process more user events simultaneously. In telecommunications, the improved failover speed ensures messaging services remain reliable, even during hardware disruptions across wide-area networks. The architectural roadmap for Apache Kafka is clear. Zookeeper is being phased out as the industry standard. Organizations prioritizing cloud-native scalability should begin preparing their infrastructure for this unified metadata model. Maintaining legacy coordination systems will eventually limit developer velocity and increase the cost of managing large-scale data streams. KRaft represents the current architectural standard for high-performance, real-time event streaming. By internalizing consensus, Kafka removes the coordination bottleneck and unifies the data and control planes into a single distributed architecture. KRaft enables data streams to scale seamlessly, powering a unified infrastructure through autonomous synchronization and native metadata management.